Hey folks, we're almost done. We are going to talk about phase changes. We're going to talk a little bit of math here. You're going to need to take some notes. You might want to use your calculator, but that's really going to be more in the next unit. This is more conceptual of what in the world happens with phase changes. And along the way to phase changes, how do we get to a phase change? All right, let's think about water because that's the easiest thing to deal with. And we think about our phases when we think about ice cubes, right? Those clearly are solids. And over here we have a glass of water, so that's a liquid. And over here we have a gas. Now, we do have, those are our three phases. Now, of course, we go through phase changes, like our solid becomes a liquid when it's melting. So we've talked about that. It becomes a liquid, and then it heats up some more, and then finally it boils, and it turns into a gas. So what temperatures are things at? Well, let us assume for purposes of argument that we are at sea level. Well, this is going to be 0 degrees Celsius. And our boiling water is going to be 100 degrees Celsius. But what about these other ones? Well, let's just take a glass of water. Do you know what temperature the water is? Well, no, it could be cold. It could be 0 degrees Celsius. It could be 99.99 or right barely touching 100 degrees Celsius. Right? We don't know. It could be anywhere in the middle. It could be 50, it could be 30, it could be 20, it could be 10. We don't know. Right? You can't tell by looking at it. Right? And this is one of the things that drives my students nuts because they look at an ice cube and they say, oh, it's 0 degrees Celsius. No, it's not. You don't know what temperature that is. You know it is no warmer than 0 degrees Celsius. But it could be 10 below 0. It could be negative 10. It could be negative 20. In fact, it probably is if it's coming straight out of the freezer because it's cold, right? And this gas over here, you don't know what temperature it is. Now, water turned to gas at 100 degrees Celsius, but what temperature is this gas? Well, when it was in the tube here, the lava tube underground, right, as it was coming up, it was touching some very hot rocks. And when that happened, the gas heated up to more than 100 degrees Celsius. So that gas coming out of there is more than that. Okay. Hopefully that helps a little bit. So when you see ice cubes, right, ice cubes are below 0. Okay, when you touch an ice cube to your tongue, if you pulled it straight out of the freezer and then put it on your tongue, if you ever try that, you'll notice it tends to stick to your tongue, right? And that's because it's freezing the moisture that's already on your tongue because this ice cube is so cold that it freezes to your tongue. And of course, if you do something stupid like put your tongue on a pole, right, you're going to find that the water gets below freezing as well, and your tongue is going to stick to the pole. Please don't do that, right? Stupid thing to do. Anyway, all right, so we know that the temperature of a glass of ice water is going to be 0 degrees Celsius. Again, we're talking at 1 atmosphere pressure, right, because that is the temperature at which ice melts or water freezes. Glass of water, no idea what temperature. It's somewhere between 0 to 100, but we don't know where it is. And boiling water, we know that that's 100 degrees Celsius. But a geyser, we have absolutely no idea. All right, so let's graph this. Right? The concept is when you have something that is ice and water, and what's going on here is we are adding heat to something. As we notice across the bottom, we're adding heat. All right? So what happens is if we take an ice cube and we pull it out of the freezer, it's very cold. And what's holding that thing together are the intermolecular forces between the molecules of water. You know that. Well, eventually when we get to 0 degrees Celsius, which is 273 Kelvin, right, the water starts to melt. And when it melts, you'll notice that this line is not going up at all right here. This line is perfectly flat, and that's because you have both ice and water present, and the temperature is going to be 0 degrees Celsius. It's not going to go up at all. Even though you're adding heat, all you're doing by adding heat is converting the ice to water. You're going through a phase change. But eventually, all the ice melts, and when you get here, all the ice has melted, and you start going up here because you have water. And now what you have is a glass of water, and you're heating that water up, and heating that water up, and heating that water up, and eventually the water gets to be 100 degrees Celsius, or 373 Kelvin, and the water starts to boil. And it boils, 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 and boils, and finally, all of the water has boiled off. And so now what you do is you take that steam that boiled off and you go and you keep heating it up, all right? And the temperature of your steam goes up, right? This is called the phase change diagram for water. Please write this down. Pause the video, write it down. Okay, make sure that you understand in this first part of the graph, from here to here, you have solid ice. During this part of the graph, you have a mixture of ice and water. Here, from here to here, you have liquid water. All right, but once you start hitting here, that water is evaporating. So you have both water and steam present, right? Both a liquid and a gas. And then up here, all you have is a gas present. All right, so we talked about the temperatures. We talked about intermolecular forces. Let me just hit that a little bit stronger. Intermolecular forces between the water, yeah, they're not as strong as they are in a solid, but they're certainly up in steam. There are no intermolecular forces at all. Remember, we treat steam like an ideal gas, and so we just say that the molecules do not attract each other at all. So we say there are virtually no intermolecular forces when it's steam. There are some when it's a liquid, and they're very strong when it's a solid. All right, you've heard this before. Fill in the blank. Higher temperature means the molecules have blank kinetic energy. What's the blank? Sure, they have more kinetic energy, higher kinetic energy, any word like that. Okay, they have more kinetic energy. They are moving faster. The molecules are moving faster. Or in the case of a liquid, they're vibrating faster. Okay. All right, we've got some numbers that we need to have, and I want to mention them. The specific heat of liquid water we already know, which is 4.18 joules per gram degree centigrade. But notice that the specific heat of ice is different. In fact, it's only about half of what it is for liquid water. So in other words, once something is ice, I can heat it or I can cool it faster with less energy than I can if it's a liquid. And if I have steam, it takes even less energy to be able to heat steam. So once it is steam already, then it's pretty easy to make it hotter. Okay, so the one that we use often is this one, the 4.18, because that's liquid water. Excuse me, and that's what we use in calorimetry, for example. We use liquid water. So we're going to use these other ones. We're going to put them in a chart in a minute. But just understand that ice and steam heat at different rates. So it takes less energy to heat up 1 gram of ice. It only takes 2.11 joules to cool or heat 1 gram of ice 1 degree centigrade. If I want to, when it's still ice, okay? We're not talking about changing from ice to water when it's just ice. When it's a liquid water, it takes 4.18 joules to heat 1 gram 1 degree centigrade. But if it's steam, it only takes 1.7 joules to heat 1 gram of steam 1 degree centigrade. Now, in every case, there's still water, right? But one's a solid, one's a liquid, one's a gas. So what we're talking about are the parts of the graph that are here and here and up here. So it takes 4.18 joules to raise 1 gram of liquid water 1 degree centigrade. But it takes, sorry, I don't remember the number, it takes 2.11 joules. It takes 2.11 joules to raise 1 gram of ice 1 degree centigrade, and only takes 1.7 joules to raise 1 gram of steam 1 degree Celsius. Okay, so that's important to realize what we're talking about. Now, we haven't talked about these guys yet here when we're actually going through phase changes, but we've talked about the parts where we're heating something up still within one phase. But what happens when we want to vaporize it, when we want to turn it into steam? Well, the amount of heat absorbed by 1 mole of a liquid as it vaporizes at a constant temperature is called the molar heat of vaporization. Notice it says molar heat. Notice again, molar heat. We're not talking about grams, we're talking about moles. All right? So to heat 1 mole of water, so it goes from being a liquid to it goes to being steam. It's still at exactly 100 degrees Celsius. We haven't changed that. But your heat of vaporization is 40.7 kilojoules per mole of water. Now, it's absorbing energy because it is getting hotter. Of course, it's sitting on a stove. There's heat going into it, so you can think of that as it is absorbing energy. So it is endothermic, right? And if you go and condense it, you get that energy back, and so it's just an opposite, so it's a negative, so that's exothermic. All right. Let's try and put that in terms you can understand. 40.7 kilojoules per mole is the same as 2.26 kilojoules per gram of water, because there are 18.015 grams of water in 1 mole. And remember, this is kilojoules, so this is 2,260 joules of energy. Let's do that again. 2,260 joules of energy to raise 1 gram. Yeah, that's right. To take 1 gram of water and convert it from liquid into steam. And all of that is happening at 100 degrees Celsius. All right, so we haven't made it any hotter. The temperature's remaining the same. It's just at 100 degrees Celsius. That seems like a huge number, doesn't it? That is a huge number. Well, let's take it one step further. Let's say that we know that it takes 4.18 joules to raise 1 gram of water 1 degree Celsius. What happens if I want to go 100 degrees Celsius? So that would take 418 joules to raise 1 gram of water 100 degrees Celsius. So we take it all the way from 0 up to 100. Sorry, that's degrees Celsius, that's not percent. Right? 100 degrees Celsius. It takes 418 joules to raise 1 gram of water 100 degrees Celsius. And look, that's 2,000 joules. Right? So it's like 5.5 times more energy to take 1 gram of water and boil it than it does to raise the temperature all the way from 0, from just above freezing, to where it's ready to boil. So it actually takes more energy to boil that liquid than it does, almost between 5 and 6 times more, to go and boil it. Now, let's look at our graph for just a second. Look at the amount of time or the amount of energy we have to add to take all of this water and convert it from 0 degrees Celsius to 100 degrees Celsius. And then look at the length of this line going from here to here, right? Where you're converting just plain water to steam and the temperature hasn't changed a bit. And notice how big this is, how wide this is, compared to how wide that is. This is really not very wide at all. And look at that. That's very, very wide. And that's because it takes so much more energy to convert water to steam than it does simply to heat it up. Think about putting a pan of water on the stove. It doesn't take long to bring it to a boil. But when it boils, does it boil off quickly? No, the water just stays there and stays there and stays there. That's why. There's your reason for why. And some numbers for why. Now notice it doesn't take a whole lot of energy, anywhere near as much energy, to melt ice. It still takes energy, a lot of energy, but nowhere near what it does to boil it. So our molar heat of fusion is the amount of heat absorbed by 1 mole of liquid as it melts at constant temperature. Now, I don't know why they did this, but to me, fusion means putting things together, and we'll talk about that in the nuclear unit later on. But for whatever reason, they call the heat of fusion meaning that it is melting. I would have called it heat of melting, but they call it heat of fusion. And it's 6.01 kilojoules per mole. It is also endothermic. We're melting ice, so it is absorbing energy out of the environment. The heat of solidification, on the other hand, is going to be negative because it's exothermic. It's giving off heat. So those are your numbers. Okay, so just wanted to have you an idea of what those are. Please note your units. Note your units are using kilojoules instead of joules, and they're using moles instead of grams. Right, so those are important. So what I would like you to do right here, this is the last slide. Please pause the video, write down this this chart, because you're going to need it in the very near future. Please make sure you write down units. right? Because you need to know whether it's joules or kilojoules and grams and moles. Okay? Okay, that's it. Do your worksheet. Oh, I'm not sure there is one. Yeah, I think there is one. Go ahead and do that, and then we will go into the math of this in the next unit. All right? See you in class. Ask us questions if you got them.